I'm going to show you a trick that's actually really cool. This is the use of something called differentials. And differentials opened up because of this new Leibniz notation in terms of expressing the derivative as an algebraic construct of dy over dx. Now, I'm going to do these two exact problems. All right, watch what happens. So y equals x squared. All right. Do you agree that dy over dx, if y equals x squared, is 2x? Now, in a quick little puff of algebra, do you agree that dy equals 2x dx? So follow my logic here for a sec, because at first it's a little bit tricky to figure out, but watch what happens. So I'm going to rewrite that. dy equals 2x dx. Now think about what this is really saying. This is saying change in y, right? And this is saying change in x. So let's go back to the first one. Remember how we said we were going to approximate, we wanted to figure out what 3.1 was. And then we approximated this to L of 3.1. Well, what these things called differentials enable us to do is they let us circumvent that whole process. Watch. I know, again, remember, I started at the point 3, 6, right? Or excuse 3, 6. Try again, ding dong. 3, 9, right? Last I checked, 3 squared. I should write all this up because I'm getting in my own way. I know that f of x equaled x squared, and I got 3, 9. Okay? So dy equals 2x dx. All I'm going to do is I'm looking for the approximate change in y. So I'm going to take 2 times the x value that we started at, the point at which we started. Remember, this is x naught, and this is y naught. So I plug in my 3, right? That's where I started. And then dx, what is my change in x? Well, if I started at 3 and I went to 3.1, doesn't that imply that the change in x, this dx, is going to equal 0.1? So I'm going to go times 0.1. Now this is equal to 6 times 0.1, which is 0.6. Now, that is my change in y. That's my change in y. Now, what do I do with that? Well, all I do, if I want to figure out what f of 3.1 is approximately equal to, I just take my y value and I add it to my change in y. Doesn't that make sense? If you start with your y and you add your change, that's your new value. Well, my y value is 9. My change in y is 0.6. And I end up with 9.6. Dun, da, da, da. Look at that. 9.6. Same value. The thing that I have to remember to do here is to take this dy and add it to my original value of y. How about for this guy? What do we get? 9.174? Same thing. So dy equals 2x dx, right? So I just go 2 times my original value, which was 3, and then my dx, which is 0.029. That was my change in x, right? Because I started at 3 and I finished at 0.029. And what do I end up with? I ended up with 0.174 if I multiply these out. So I know that f of 3.029 is going to be approximately equal to y plus the change in y, which the original y was 9, plus the change, which is 0.174. Isn't that cool? Okay, now watch. Let me show you why differentials are so cool. Sometimes writing a linearization of a function can be really, really hard. Watch this. Do you guys all agree that the volume of a sphere is equal to 4/3 pi r cubed? Okay? Now, I simply want to approximate. I want to know what is the volume of a sphere of, let's say, radius 4.01. Okay? Now, I realize in the face of technology, it's very easy to put 4.01 into our calculators, cube it, multiply the whole thing out. All right? I realize that. However, think before technology and really understand that we're going through a mental process here. Watch. I don't want to do a linearization of this because it's going to have pies and all kinds of garbage out there. But what I am going to do is I'm going to differentiate. I'm going to use differentials. I'm going to differentiate v as a function of r, because it really is. If I multiply all that out, I end up with 4. Notice my 3's will cancel, and I'll end up with 4 pi r squared. Strangely enough, that's the surface area of a sphere as well. Now, I know that dv is going to equal 4 times pi times r squared times dr. Now, let's just slow down here. Now, this works for every single sphere because all spheres have this volume, and they're going to have this differential set up. Okay? Now, look at the radius. The radius is 4.01. What's the closest whole number that's easy to work with? 4, right? Well, let's think about this for a sec. If I'm thinking about a point, really what I'm thinking about is, I'm going to put 4 in for r, right? And what am I going to get here? Excuse me, I'm going to get 4 cubed, which is 64, times 4, which is what, 256? So it's really 4 to the 4th. 16 times 16, which is 256 thirds pi. So 256 thirds pi. All right, so I have the point 4, 256 pi thirds. All right, everybody agrees with that, hopefully. So think of this as r, and this is v of r. All right, now watch what happens. I'm going to solve for my differential. All right, so I've got 4 pi r squared, so it's going to be 4 times pi times r squared, which I started at 4. There's a lot of 4's floating around, but we're not afraid. And then what's my dr? What's my dr? Well, this is squared, by the way. It's 0.01. So my change is going to be this. Let's see. 4 squared is 16 times 4 is 64. I end up with 64 pi times 0.01, which, I mean, if you think about that, that's 1/100th times 64. Doesn't this just end up being 0.64 times pi? That is my change in volume. However, if I want to know what the volume of 4.01 is, well, it's the original, remember this is going to be the volume plus the change in the volume, which is equal to 256 pi thirds plus 0.64 pi. Now, if I wanted to clean that up, I suppose another way that I could write it up is 256 pi thirds plus 64 100ths pi, right? And then I could find common denominators and do all that nasty things. But notice it's doable by hand. Back in the day, it was really hard to cube a number like 4.01. Now, that's just an example of how you can use differentials. Again, differentials are so much simpler to use than the linearization. Remember using the line to approximate the curve. But it's the linearization. We could have done linearization here. It just would have been a little bit uglier. Okay? All right. I hope you enjoyed that. We're going to do a bunch of these tomorrow in class, so don't panic. Enjoy, and I'll see you tomorrow. Have a